send her the hardcover as a gift, and hope that you'll take it into her side.
Hello everyone, welcome back to the second part of this tutorial. The simulation finished. It took a little bit less than 3 minutes for it to run. And now I will open up this case in ParaView. So not the 1000 cell case, but the 10,000 cell case. I apply it, and now it's again located here. So I will translate it. Now it's down here. I want to show you the velocity and the mesh. And you see that I even have to scroll in because we do not see anything. And now you see that this mesh is rather fine. Again, one cell is made up by 10 cells here. And one cell here has the length of 1 millimeter. Now you see that this discontinuous jump is smeared over 1, 2, 3, 4, 5, maybe 6 cells. But this discontinuity has the length of 5 to 6 millimeters. And in the other cases, the discontinuity has 4, 5 centimeters or 30 and 40 centimeters. So this is closer to a real discontinuity. Now, but if I zoom out and get rid of the grid, now you see that this really looks like a discontinuity. And of course we could change the discretization schemes, but we will not do that. I want to show you the influence of only the mesh here. I also want to show you how you can export lines out of your geometry. I already showed you this possibility in the first tutorial with this plot over line. But you can do that outside of ParaView in OpenFOAM. And for that I want to talk a little bit about this sample dictionary. Because you have a command called sample with which you can sample through your geometry. And here I just define one line that is going from more or less -5 to +5 in the center of our geometry. And I want to use 10,000 sampling points. And I want to sample through the temperature, the magnitude of the velocity and the pressure. Okay, so I save this, and I want to show you all the folders. And as you see, in the first folder we have this mag-u value, but we do not have the magnitude of the velocity in the other folders. For that I will use the foamcalc utility, which calculates the magnitude of the velocity. And now if you take a look, now we have this mag-u file in all the folders. And now I can sample through them. I type in sample, and now you see that there is this post-processing folder. If I go into that folder, there's a sets folder, sets, and now we have the results between 0 and 7 milliseconds. And in all the folders we have one file called data_mag_u_p.xy, and these files you can use as input for your tool of choice, Excel, GNU plot, whatever you want. I want to import them in LibreOffice, but LibreOffice doesn't really understand this .xy extension, so I will have to change that. And I will only use the results of 7 milliseconds. So if I open up this file, this is a text file with 4 columns with the x coordinate in our geometry from -5 to +5, and the temperature at the given x coordinate, the velocity magnitude, and the pressure. So I will do the same now for the other two cases. 1000. In the sample dictionary I will go for 10,000 sampling points, so I have the same x coordinate for all the 3 cases. At first I have to calculate the magnitude of the velocity, and now I can sample through it. You see there is the post-processing folder, and for 100 cells I will do the same. 10,000 points, of course this is an overkill. FoamCalc mag U. Good, now sample. And what I will do is, at first, for the sample dictionary there are different possibilities other than a simple line, and you'll find in your user guide, which is located in in your OpenFOAM folder under doc. So open it up on page 273, and here you see all the possibilities that you can use for sampling. For example, with cloud you can get out the values at specific points in your geometry. So go through that. But now for the comparison I will copy these data _t _magu_p.xy files from all the folders to this folder, to the laminar folder, and I will open them up here one by one in LibreOffice. So I copy from the Shock2 100 cell case tutorial, from post-processing sets, and after 7 milliseconds the data file to here. Now you see we have it here, and I will rename it with mv to _100, so I know that this is the file with 100 cells, .csv, so LibreOffice opens it. I will do the same for the 1000 cell case and rename it. If you take a look, now we have this here and the results from the 1000 cell case. I rename it. Now you see 100 and 1000, and I do the same for the 10,000. Okay, and I will rename it. Oh, I have these 3 files here, and these I want to open up in LibreOffice. Open. I'm in the correct folder, but navigate into OpenFOAM, tutorial compressible sonic foam laminar. I open up the 100 cell case. Okay. And here you see the x coordinate, temperature, the velocity magnitude, and the pressure. I will do the same for 1000 cells. Okay. And I will just copy that here to the 100 cell case, so we have it in one file. I exit, I close this file, I open up the 10,000 cell case, I will copy that again into this file, I close this, and now we have the results for 100, 1000 and 10,000 cells. Since I put in 10,000 sampling points in all the sample dictionaries, we have the same x coordinate till 5. So I will delete this and this. I will delete the columns also. And now we have all the temperatures, the velocities and the pressures. And I will plot now For example, let's start with the pressure. In one diagram. And now you see this is the result. And you see that the results are converging towards this discontinuity. If I show you the velocity magnitude, okay, so let's make it bigger. And I want to zoom in, for example, 3.8 and 4.2. Now we only see the shock wave, the discontinuity, and you see with 100 cells we cannot depict discontinuity. And with the refinement of the mesh, this is really getting close to a discontinuity. But if you go back, the question is, what are you interested in? Are you interested in this maximum velocity or really the shock? Maybe for your case 1000 cells are enough, but maybe not. Maybe you really want to depict this shock here, then you might need 100,000 cells or 1 million cells. But with that you will increase the calculation time. So it's always a compromise between resolution and runtime of your simulation, and you have to decide how fine your mesh has to be. But additionally, if I show you also the temperature, if your mesh is too coarse, for example here with the 100 cells, then here you have these weird oscillations in the temperature. And as I mentioned, what's physically happening here in the compressed gas on the right hand side, the temperature is increasing because of the compression, and on the left hand side in the originally high pressure gas the expansion occurs and here the temperature drops, and you do not depict the correct temperature here because of the mesh, because your mesh is too coarse and you have these weird oscillations. So you always have to think about your grid. Okay, I want to show you one additional step. I want to change the pressure difference from factor of 10, so 10,000 and 100,000 to 10,000 and 1 million. And for that I will copy my base case. I may make a copy of that to shock tube underscore high pressure, and I will enter this. I have everything. Now I will change the number of cells to, let's just say 1000 at least. Okay, and I want to change now also the pressure difference. So instead of 10,000 and 100,000, I want to have pressure difference of 100. So I'm changing this value to 1 million. I save this and I make the mesh and I execute set fields. Good, and execute sonic foam. Very good. You see that the maximum Courant number is not 0.29, but it is higher, so there is a definite change here. Let's just go to ParaView and open up this high pressure case. And it's again located here, so I will translate it, but now I will translate it to the positive y direction. So we are having it up here. I will show at first the pressure. Let's just go back to 0. Here. And now you see that for this case, the pressure difference is 100. So we're going from 10,000 to 1 million instead of 10,000 and 100,000. And if I show you the shockwave, now you don't see it. If I zoom into 10,000 and 100,000, you see that the shockwave with the higher pressure difference is traveling at a higher speed. And actually after 6 milliseconds it reaches the boundary. So I will just evaluate the results after 5 milliseconds, and I show you now the velocity. So a change in pressure from 10 to 100 increases the velocity. Before it was between 0 and a little bit less than 300, and now it's between 0 and a little bit less than 600. So the change of in the pressure of a factor of 10 only increases the velocity by a factor of 2. Okay, so what I would suggest you is that you do these simulations with a pressure difference of 100 for the 100 cell, for 100 cells, for 1000 cells and 10,000 cells. You export them on your own as a homework, and you take a look at the results in one diagram. And you, as I mentioned, you can also play around with set fields with the sphere to cell and cylinder to cell possibilities, also as a homework. And after that, you should be able to use set fields. Okay, so this concludes the second part of the tutorial and also the tutorial itself. I hope you enjoyed it and that you learned something. I thank you for watching, and I hope to see you next time.